let me discuss these issues one by one. This will be very useful, that in a product what are the quality issues, what you can see actually as a problem or a defect in a product. Normally they can be manifested, as I have told you, either as a surface itself, that means visible imperfection. It can be a surface lamination. Lamination means, I have mentioned, it is like two different surface. On the surface some additional surface has been generated, that is called lamination. Sometimes some people call it a shell type of defect. So it can be a surface lamination or shell. It can be a very thin line on the surface of the product, particularly in a cold rolled product. See, it is called a sliver, that means it is a very thin line of defect. Normally it has been found to be associated with some slag entrainment at different stage of the sample preparation, or maybe either during casting. So some slag got entrained, or even in tundish there is a possibility of entrainment, or even in ladle there might be entrainment. So finally that slag is, if it is has a good formability, so it will be manifested as a thin line which is called a sliver. So either it can be a surface lamination which is called shell, or it can be a thin line which is called a sliver, or there can be cracks or holes on the surface. That means you find in the cast product there are certain cracks or maybe small holes. So these are really very crude defects. So we have to know why this has formed, at what stage it has formed, and then these are on the surface I am talking about, and there can be certain problems at the subsurface or internal defects, which normally you do not see on the surface. Through a non-destructive testing you can see, or if you have cut a cross section, then you can see. Sometimes you have to see the cross section, as I have told you, in cast product the internal defects you can see only in a section, in a cross section. Surface may be alright, but if you cut a section, take a section view at different stages, then you will find some defects may be there at the subsurface, some defects may be at the interior, some defects may be at the central location, central line. So all this central line you do not see on the surface, so you have to see at the section, cross section. So subsurface or internal defects also are sometimes manifested, but accordingly you have to see at those sections, then only you can see them, their manifestation. Now genesis, as I have told you, it can come from the input cast material. So if it comes from the input cast material, then what are the possibilities? I have told you the two broad categories. Either they are exogenous entrapment from steel making or casting. That means steel making means either during secondary refining, or during in the tundish from the ladle, or during casting itself from the mold there may be entrapment, mold slag may be entrapped. There are other possibilities of entrapment also. So this is one. Or from the subsurface imperfection in casting there may be a problem. These are normally surface imperfection in casting. These are basically entrapment during steel making or casting, that means exogenous entrapment. But another source is the casting quality itself, that means there may be some imperfection on the subsurface of the casting, which are finally generating in the final product. So normally it can be grade specific, that means certain grades will generate certain quality issues, or from the process itself, from the casting process itself, if there are certain irregularities, then you might get some defects. So these are the possible issues. Now what is important is identification of the root cause, that means the genesis is essential for implementation of remedial measures. Maybe you are getting certain defects, you want, why do you want to know the genesis? Because if you know the genesis, then you can take care of it in subsequent stages. Say defect has formed at particular instance, you do not want the defect to continue in subsequent stages also. So if you know what was the root cause of the defect, what was the genesis of the defect, specific reasons you have to identify, then in subsequent processing stages, subsequent steel making, secondary refining or casting stages, or even reheating stages, you can take care of it. So that is why it is important for identifying remedial measures, what are the improvement measures, how do you improve it, this is very important. Now, I will just talk about a few typical defects which can form in the final rolled product, which are starting from the casting product, but after rolling only some of the defects you can identify. Sometimes particularly this happens from in stainless steel. Certain stainless steel you find that the edge of the rolled product, hot rolled product, there is some crack formation at the edge. We call it edge crack. So, normally it has been found that there is a chemistry balance problem between delta and gamma. That means in certain grade of chemistry, if say 304 is a common stainless steel grade, I have talked about this. The nickel equivalent by chromium equivalent of this grade is around say 0.55 only, the periodic, so called periodic chemistry we call it. But if the nickel equivalent by chromium equivalent is very low in this grade, that means it is going slightly towards the ferritic range, then what happens, your continuous casting quality will be relatively better. As I have told you, you increase the nickel equivalent by chromium equivalent, or rather you decrease the nickel equivalent by chromium equivalent to make it slightly ferritic, so that the delta ferrite to austenite solidifying takes place below the peritectic temperature, below the end of solidifying temperature. But in that process, if you do not have much control, then what will happen is, if the delta ferrite becomes more strong, then you might have edge crack. That means normally in 304 your ferrite at room temperature at slightly higher temperature should be around 4 to 5%, but if it exceeds 6%, if it becomes say 8% or 10%, then you have this problem of edge crack. So, basically chemistry can play a role here, chemistry balance is very important, or what is important here is nothing to do with the chemistry or continuous casting, is the hot rolling parameters, like what are the type of hot rolling mill you are using, it is a Stekel mill or normal hot strip mill, those are important. What are the temperature, finish temperature, that is important. If you roll at low temperature, the problem of edge crack might be there. If you roll to very thin thickness, there might be this problem. So, if you have a relatively high amount of delta in this particular grade, there is a problem. So, chemistry is important from the product quality point of view, and from the processing point of view, type of mill and the thickness and the rolling temperature, these are important. Then if you come to the defect, we call it shell or surface lamination. This is a very typical and very recurring problem in hot rolled materials, hot rolled coil or even cold rolled coil. So, you will find this laminations, surface laminations. Now, as I mentioned to you, proper surface inspection is very important to identify at where these laminations are taking place. Are these laminations taking place near the edge? If it is near the edge, normally it has been found that it may be related to the chemistry, or it may be related to the hot rolling problems also. It is related to chemistry means, as I mentioned, for 304 grade, I have given an example that there was a lamination, and just below the lamination at the subsurface there was a crack. So, these laminations near the crack, near the edges, are coming from defects, cracks, or depressions, longitudinal depressions near the edges for grades which have the so called peritectic grades, that is around 0.1% carbon or 304 stainless steel. So, it is chemistry related, that means here. So, we can control it, as I have told you earlier, by adjusting minor adjustment of chemistry. So, if it is coming from mill, you have to tackle it in a different way, which I am not discussing in this particular session. So, now in shell you might find that only you are having some scale, and there is a change of microstructure like internal oxidation or grain coarsening. Then the defect was existing at the subsurface of the concast material. As I was telling you, always or maybe sometimes when you have a depression defect, just under that in subsurface there might be crack. During hot rolling, that crack is coming to the surface of the product. So, then what happens? Then you get internal oxidation, because that crack which is getting exposed during hot rolling, so will get oxidized. So, we call it internal oxidation, or if the crack from the surface it is going inside. So, that means there is ingress of oxygen during rolling or during reheating. So, we call it internal oxidation. So, you will find scale, we will find some microstructural changes like grain coarsening, like internal oxidation. So, you know the defect was existing in the cast product itself at the subsurface level, then only these signatures you will get, internal oxidation, scale, grain coarsening in the final roll product. So, we know if defects are present, that means it has originated from the continuous cast material, or it might be imparted during the early stage of hot rolling also. So, again you have to, this is important, at what stage, whether it was from continuous cast material or imparted during hot rolling, that is important. But since we are concerned about the product quality here, the quality which is coming from the cast stage itself, we have to be more careful about that such defects do not exist in the cast material. If there was a crack formation during hot rolling, I mean due to say low temperature rolling, there might be a crack formation, that is a different aspect, we have to take it, take care of it during hot rolling. But if there was a crack, subsurface crack existing in the cast material which got exposed during hot rolling, then the culprit is not hot rolling, it is forming during hot rolling, but the culprit is crack existing in the pre-existing in the cast material itself. So, we have to identify at what stage this defect was generated, that is very important. Now, there might be this shell in a location of this surface lamination anywhere on the cold width, not any particular location. So, normally it can be due to large NMI, or it can be due to mechanical damage during cold rolling processing or not. So, if it is due to large NMI, that means the steel makers are responsible for it, and the rolling mill people are cannot be held responsible, because it is because of large non-metal inclusions which have got entrapped in the steel either during steel making or casting stage. So, this might generate randomly at any location of the final roll product. So, if it is near edge, then we know it may be due to lamination, or it also may be due to hot rolling, they use ager. So, because of ager problem also it might take place. So, from the signatures in the final product, in the rather a defect analysis, you can know at what stage it has originated. So, that is very important. If it has originated during steel making or casting, then you have to do something, you have to take care of it in a certain way. If it has originated during processing, then subsequent stages you have to take care of. So, again I am repeating that proper defect analysis is very important to know at what stage the defect has been created, and from there with prior knowledge you have to correlate why it has been created, so that subsequently you can take care of it. Now, sliver, as I was telling you, is another type of defect. It is basically, some people call it a slag line, because it is basically entrainment of slag. It can be either from ladle or tundish or mold. It is normally, it happens not towards the edge of the rolled product, normally in the middle portion of the width of the product. Normally it has been found to happen, and whether it is from ladle or tundish or mold, as I have told you earlier, you can identify this when you analyze through EDX or WDX. Whenever this slag line is there, you cut a small sample, put it on the scanning electron microscope, focus the electrons on that defect and see what are the elements present there. If it is from the ladle, it will have predominantly calcium, that means it is basically calcium oxide, rich in calcium oxide. Other oxides also will be there, but relatively less. If it is from tundish, predominantly silicon oxide will be there. So, silicon concentration will be relatively more, silicon oxide. If it is from mold, you will find some calcium fluoride, or you might find some sodium oxide. So, those will indicate the slag is coming from the mold or it is standish or from ladle. So, this slag entrainment gives a defect which is normally called sliver or a slag line of defect, because it is basically coming from entrainment of slag during either during secondary refining or continuous casting. Now, sometimes as I was telling you, there might be a tearing or a hole generation of hole in the product, but normally it has been found that it has nothing to do with the cast product, it is mainly due to cold workability problem. That means when you are deforming heavily worked grains, that means too much of cold deformation might generate tearing or hole. So, the continuous casting people or the steel making people are not responsible for it. So, I am not discussing in details this problem, is something to do with the cold rolling. Now, we might find transverse crack. Now, I have mentioned earlier this transverse crack is mainly generated due to transverse defect existing at surface location of cast product, whether it is slab or bloom or billet. This transverse crack, as I was telling you, it can generate from transverse depression or deep oscillation marks. Deep oscillation marks are basically having a transverse orientation. So, under those deep oscillation marks there might be cracks in the subsurface region. So, when you are finally rolling that product, those cracks which are just below the transverse depression, they will come to the surface. So, you will find transverse cracks or defects generating in the product after rolling, but they were existing at the subsurface locations, either at the root of the deep oscillation marks. Along with transverse cracks, you might find some powder entrapment also. So, cracks along with entrapment. Sometimes you find crack, you do not find any entrapment, whether it is from slag or alumina, any other sources, or even refractory erosion. These are the common entrapments. Sometimes you find only crack, sometimes you find crack associated with entrapments. That means the entrapment was possibly responsible and then crack has formed. Sometimes you find only crack, no entrapment, and crack means there will be some internal oxidation because when the crack comes to the surface, some oxygen will get inside. So, you will get some scale, you will get grain coarsening, you will get some internal oxidation. So, whether cracks are present on its own or cracks are present along with entrapments, large entrapments, that is what is important to identify what is the genesis of the problem. Now, again I am telling this material defects, what basically this course is related to. This course is related to material defects and not processing defects. They are basically originating in principle from the parent cast material. So, defects existing either at the surface or subsurface of the cast product, whether it is slab or bloom or billet. They might be related to the chemistry of the grade, that means their location, their formation. I am not telling the chemistry is related directly, but what I am telling is the grade. Because of the particular grade, certain type of defects are created. So, that way the grade is responsible, or they might be influenced by the casting parameters themselves. Some are grade specified, grade related. As I have told you, this laminations are basically coming from, sometimes the surface laminations, sometimes that is coming from depressions. I have told you those laminations which are located near the edges, they are coming from certain specific locations, that means specific depressions which are originating from particular grades like 0.1% carbon, the so called peritectic grade, or 304 stainless steel, the so called again peritectic grade in stainless family. So, their grade is playing a role because the delta to gamma transformation I have mentioned several times is taking place at a crucial stage of solidification. So, by slight adjustment of chemistry you can take care of this problem. So, here chemistry of the grade is, that is why important. You can slightly adjust the chemistry and take care of this problem. and sometimes the problems are due to casting parameters as also. That means suddenly there is a fluctuation in mold, suddenly there is a suddenly there is a casting speed change, then it is due to casting parameters, nothing to do with the grade. So grade is important because grade will dictate, as I mentioned earlier, how the solidification will take place, whether sticking will be there or depression will be there. If there is sticking, then you have to tackle it in some way, I have mentioned earlier. If it is depression, you have to tackle with adjustment of chemistry, with adjustment of mold powder, so that the heat transfer is controlled, heat transfer is uniform. So that way the grade is important, but casting parameters first, you should decide on the grade. Also casting parameters as such, if there is some irregularity, that might generate some defect. So both are important, that is why I am mentioning the defects existing at surface or subsurface of cast slab, it can be due to both. Then another important source, as I mentioned, are entrapment of large exogenous NMI during steel refining or casting. So this is one source, another source is defect as such, that means crack, lamination, whatever. So your central segregation, central crack, these are happening due to continuous casting. But if there are large exogenous NMI, that means if there is reoxidation during secondary refining, if there is entrapment of nozzle clogged product, that is a problem. Nozzle clogged product is basically what? Alumina mainly. Then slag, as I mentioned several times, then refractory erosion. So these are all sources of exogenous entrapments or NMI, which can create material defect. So two broad categories, either exogenous entrapments large or cast defect, whether crack or other surface defects like deep oscillation marks or depressions, these might create problem. So two broad categories of material defects, entrapments and surface, cast product, defects in cast product. This I had mentioned one stage that critical size of inclusion is important, because in steel, any steel, even in very clean steel, you will find many small inclusions. We need not worry about small inclusions, as I am trying to tell you, because I have mentioned that 1 kg of clean steel, they might contain you see 10 to the 7 to 10 to the 9 inclusions. That means about 1 crore of inclusions you might find in 1 kg of clean steel. I am not talking of a dirty steel, I am talking of clean steel. But fortunately, most of these inclusions are very small, which is called it benign, that means less harmful. Only few are large, say about 400 are about 80 to 130, only 10 is about 130 to 200 micron, only 1, the probability of such big inclusion is only 1 or less than 1. So we have to worry about only large inclusions, which are very few in numbers, but they might be, if large inclusions present, they might create problem. So inclusions as such is not a problem. Large inclusions and too much of large inclusions is a problem. So average volume content of inclusion is not important. You might find one particular steel is relatively clean, the volume content of inclusion is less than 0.1, but certain inclusions are quite large in size. So we have to worry about that, because those inclusions will generate defect. So average volume content or average size is not important. What is important is whether some large size inclusions are present or not. So number and distribution of large inclusions, they normally come from exogenous sources. From endogenous sources, that means deoxidation products, they are normally smaller in size. But reoxidation, that means when oxygen enrichment is taking place afterwards, that means when steel is exposed during its transfer from say ladle to tundish or tundish to mold, that is called reoxidation. Those are the inclusions which are large in size. Then I have mentioned what are the sources of large inclusions. Slag they are normally large in size, slag entrapment or entrainment. The refractory erosions, they are large in size. So we have to really worry about those large inclusions which are say 100 micron or more, or 70-80 microns or more. These are the inclusions we have to be careful about, and not very small inclusions.